Welcome to NPTEL MOOCs course on Machine Learning and Deep Learning, Fundamentals and Applications. In my last class, I discussed the concept of linear support vector machine. We considered that the training samples are linearly separable. For designing of the support vector machine, we considered a parameter. The parameter is margin width, the width of the margin. And based on this parameter, I have designed the support vector machine. So I have to solve one optimization problem, and while solving this optimization problem, I define the support vectors. Support vectors are most informative points of the training dataset, and based on this support vector, I can determine the weight vector. So after getting the weight vector, I can determine the discriminant function, and with the help of the discriminant function, I can take a classification decision. In the expression of the discriminant function, you can see I have considered the dot product between the support vectors and the test sample. So it is mainly the dot product between the support vectors and the test samples. And based on this, we can determine the discriminant function. And after determining the discriminant function, like I have explained previously, so we can take a classification decision. Today I am going to discuss about the nonlinear support vector machines. That means the training samples are not linearly separable. So for this I have to design the support vector machine. So let us discuss about the concept of the support vector machine and how it can be extended for nonlinear training samples. That is, the training samples are not linearly separable, and how to design the support vector machine. So let us start this class. So in my last class, I have shown the concept of the large margin linear classifier. Large margin linear classifier. That is actually the linear support vector machine. So in my last class, I discussed about this. So we have determined the width of the margin like this, the width of the margin that is M is equal to 2 divided by W norm. So that already I have explained, and based on this margin width, I have defined the optimization problem. The problem is minimize one by 2 W norm square subject to the condition yi W transpose xi plus b greater than equal to 1. So we have defined this condition, and based on this we have formulated the Lagrangian function. So the function is minimize the Lagrangian function LP W b alpha I, that is equal to 1 by 2 W norm square minus lambda, it is from I is equal to 1 to n. Alpha I is the Lagrangian's multiplier, yi W transpose xi plus b minus 1 subject to the condition alpha I greater than equal to 0. So this alpha I is nothing but the Lagrange's multiplier. After this, what we have considered for solution of this, we have determined, that is, we are differentiating LP, that is the Lagrange's function, with respect to the weight vector and equating it to 0, and corresponding to this I have obtained the weight vector like this. Weight vector is nothing but summation over from I is equal to 1 to n alpha I yi and xi. So we obtain W like this, and another condition also we obtain by differentiating LP with respect to the bias B and equating it to 0. So we obtain another condition. That condition is the summation from I is equal to 1 to n alpha I yi is equal to 0. So these two conditions I am getting. Conditions means W I can determine, and another condition is summation from I is equal to 1 to n alpha I yi is equal to 0. And for this Lagrangian optimization problem, we considered this Lagrangian dual problem. So from this actually we have obtained the criteria maximize summation alpha I is equal to 1 to n minus 1 by 2 summation I is equal to 1 to n j is equal to 1 to n alpha I alpha j yi yj, and it is a dot product between xi and xj. So that means xi transpose and xj. So this is a dot product between xi and xj. So subject to the condition alpha I should be greater than equal to 0, and another condition is summation I is equal to 1 to n alpha I yi is equal to 0. It is the Lagrangian dual problem. So this actually we obtain like this. So if I put the values of this W here and considering this condition, the summation alpha I yi is equal to 0, then I will be getting this form, that is the Lagrangian dual problem I am getting. So just putting the value of W and this condition in this equation, so I will be getting this expression. So in this case I have to maximize this quantity, so I have to maximize this one alpha I. So alpha I is nothing but the Lagrange's multiplier, and already I told you for the support vectors alpha I is not equal to 0. So that means alpha I is greater than equal to 0. That is for the support vectors. And what is the advantage of the dual problem? Because the dual form we are considering, because this optimization criterion can be expressed as linear products of pattern xi. So what is the importance of the dual form? The importance is that this optimization criterion can be expressed as inner products of the patterns xi. So that is the importance of the dual form. After determining this, we obtain the discriminant function gx. So moving to the next slide, because already we have determined the weight vector, and from this we can determine the discriminant function, that is the linear discriminant function W transpose x plus b. So summation I, that is for the support vectors, alpha I xi transpose x plus b. So we obtain the expression for the discriminant function gx like this. So here you can see what is actually the meaning of this expression. So you can see how actually we do the classification. You can see the discriminant function is nothing but the dot product between the test point x and the support vector xi. So you can see this is nothing but the dot product between the test point x and the support vector xi. And already I told you these support vectors are the most informative points of the training data set. And corresponding to these support vectors, this Lagrangian multiplier is not equal to 0. That means for the support vectors, the Lagrangian multiplier lie on the hyperplanes. So this is the final expression for the Gx. So this classification, the classification relies on a dot product between the test point is x and the support vector, the support vectors xi. So also one important point is, for solving this optimization problem, what actually we need to compute? We need to compute the dot products xi and xj between all pairs of training points. So that is also one important point. So whenever I want to solve the optimization problem, I have to compute the dot product between xi and xj between all pairs of training points. So for support vectors, this alpha I is not equal to 0. That is, the Lagrange's multiplier is not equal to 0. And these support vectors lie on the hyperplane, and they are the most informative points in the dataset. And if I consider other patterns, suppose if I consider for other patterns, alpha I will be equal to 0, and if I moved around, they do not affect the solution of the separating hyperplanes. So that means only we can see the support vectors because they are the most informative points in the data set. So if any other points with alpha I is equal to 0 are moved around, they do not affect the solution for the separating hyperplane. So that is the fundamental concept of the support vectors. So let us consider now what will happen. Suppose if I consider this data is not linearly separable, and suppose I have noisy data or maybe the outliers. So whether this model can be modified or what is the modification I need to do, that point we need to consider. So let us move to the next slide. So now what we are consider, suppose this data is not linearly separable, so that point also I will be explaining later on. For non-linearly separable data, I have to consider non-linear support vector machine, or maybe something like if I consider noisy data, outliers, etc. So for this, what modifications I need to do? So already I have defined the support vector machine. Now I have to consider this point. The data is not linearly separable, and maybe we can consider the noisy data or the outliers. So before going to that point, that is the non-linearly separable data, first I am considering the noisy data or the outliers. After this, I will be explaining the concept of the support vector machine for the non-linearly separable training data. So for this case, that is case is the noisy data and the outliers. What we are considering? We are considering slack variable. We are considering slack variables. That is xi. So slack variable xi is considered to allow misclassification of the difficult or the noisy data points. So in the figure you can see, I can show the difficult points. So this is a difficult point, one difficult point, and similarly I can show another difficult point, and that is the noisy data or noisy sample points or maybe the outliers. So corresponding to these 2 points, there will be misclassification. So to consider this misclassification, we are considering one slack variable, and that slack variable is the xi. That is, we are considering to consider the difficult or the noisy data points, because the misclassification take place because of these data points. So I have, in the figure I have shown these two data points. You can see number 1 I can show, or number 2. So these data points are not correctly classified by earlier designed support vector machine. So corresponding to this case, my formulation will be minimize one by 2 W norm square plus C, one parameter we are considering C, I is equal to 1 to n and xi I, such that we are considering yi W transposed xi plus b greater than 1 minus xi I, and this xi I should be greater than equal to 0. So this parameter C can be considered as a way to control overfitting. So I am writing here, the parameter C can be viewed as a way to control overfitting. So you can see, after considering the slack variable xi, we have considered the optimization problem, that is the formulation I have shown, minimize 1 by 2 W norm square plus another term we are considering because of this noisy points. So this term we are considering in addition to the earlier term, the 1 by 2 W norm square, and that is actually this xi 1 or xi 2. This is actually some offset we are considering. So I can consider as offset, so xi 1 or xi 2. So in the formulation I have included that one, and based on this formulation we can also consider the Lagrangian dual problem. So move to the next slide. So considering this, the formulation will be Lagrangian dual problem. So maximize I is equal to 1 to n alpha I 1 by 2 summation I is equal to 1 to n j is equal to 1 to n alpha I alpha j yi yj xi transpose and xj. So you can see it is a dot product between xi and xj. So this is the formulation, that is the Lagrangian dual problem corresponding to this formulation considering the slack variables, and the condition is such that this alpha I, that is the Lagrangian multiplier, lies between 0 and c, and also another condition, the summation of alpha I yi for I is equal to 1 to n should be equal to 0. So that is the only modification we have to do if I consider the slack variable xi, and this I have done only for the noisy data or the outliers, but for the non-linearly separable data we have to consider the nonlinear support vector machine. So let us discuss about the nonlinear support vector machine. So this problem or this solution I am considering only for the noisy data or maybe the outliers. So for non-linearly separable data I have to consider the nonlinear support vector machine. So move to the next slide. So now the concept of nonlinear support vector machines. Nonlinear support vector machines. So let us consider the figure number 1, that is the first figure. This is figure number 1. So in this case, what we are considering in figure number 1, data set that are linearly separable with noise. So in the figure number 1 we have considered that one, and in this case we can employ the support vector machine that we have explained earlier. But if I consider the figure number 2, you can see here in the figure number 2, these samples are not linearly separable. So it is very difficult to find a decision boundary between the samples of the two classes, and these samples are not linearly separable. So that means figure number 2 I can consider non-linearly separable data. That is the figure number 2. So corresponding to this, what is the solution for this? If you see the figure number 3, in figure number 3, what we are considering, mapping of data to a high dimensional space. So just I am doing the mapping of data to the high dimensional space. So in the low dimensional space, this data is not linearly separable, but after the projection into the high dimensional space, these samples will be linearly separable. That means what we are doing, this mapping of data to a high dimensional space. So from the low dimensional space, I am mapping into the high dimensional space, and that is the fundamental concept of the nonlinear support vector machine. So in my next slide, I can show that concept. So what is the nonlinear support vector machine in the feature space? So in the figure you can see in this slide, just I am doing the mapping from the low dimensional space into the high dimensional space. So this is a nonlinear support vector machine, SVM, and we are considering the feature space. So the idea is, you can see the original input space can be mapped to some high dimensional feature space where the training samples is separable. So in the figure you can see this is the low dimensional space, and I am doing the mapping by considering some mapping functions, the mapping of the low dimensional data into the high dimensional space. So it is the higher dimensional feature space. So that means I can write the concept here. The concept is the original input space can be mapped to some higher dimensional feature space where the training set is separable. The original input space can be mapped to some high dimensional feature space where the training set is separable. So in the figure you can see I am showing the mapping function, and with the help of this mapping function I am projecting the low dimensional data into higher dimensional feature space. So this is the concept of the nonlinear support vector machine. So whenever I do the projection into the higher dimensional feature space, the samples will be linearly separable. So you can see in the figure the original data is not linearly separable, but after the projection the projected data will be linearly separable. That is the fundamental concept of the nonlinear support vector machine. So mathematically how to consider this case? So let us move to the next slide. So what is the discriminate function now? So the discriminate function, by considering the mapping Gx is equal to W transpose phi x plus B, that is equal to the summation I, actually we are considering the support vectors alpha I, and we are considering the mapping function phi xi transpose phi x plus B. So you can see the modification in the discriminate function. So what modification you can observe here? Only this term we are considering the mapping. So earlier it was a dot product between xi and x. Now we are considering the mapping function phi xi transpose phi x. Now in this case no need to know the mapping explicitly, because we are only considering the dot product of the feature vectors in both the training and the test. I repeat this, no need to know this mapping explicitly, because we only use the dot product of the feature vectors in both the training and the test. So corresponding to this, what we can consider? So we can consider a kernel function. So now a kernel function can be defined as a function that corresponds to this dot product of the two feature vectors. So I can write a kernel function can be defined now as a function that corresponds to the dot product of two feature vectors. In some expanded feature space. In some expanded feature space means some high dimensional space. In some expanded, that is the higher dimensional feature space. So that means to consider this one, we are defining a kernel function. What is the kernel function? The kernel function is k xi xj is nothing but phi xi transpose and phi xj. So to consider this one, the dot product, we are considering a kernel function. The kernel function is something like this. So I can give some of the examples of the kernel functions. So commonly used kernel functions, I can give some examples. So maybe in the next slide I can give some examples. So some of the commonly used kernel functions. Maybe we can consider the linear kernels. So one example is the linear kernel k xi xj is equal to xi transpose xj. This is the example of the linear kernel. Maybe we can consider the polynomial. So in the polynomial kernel we can consider xi xj is equal to 1 plus xi transpose xj to the power p. So this is the expression for the polynomial kernel, and one popular kernel is the Gaussian kernel. Gaussian, or it is also called the radial basis function. This is called RBF, radial basis function kernel. This is a very popular kernel. So the concept of RBF I will be explaining later on whenever I will discuss the concept of the artificial neural network. That time I will explain the concept of radial basis function. So the expression for this xi xj is equal to exponential this is xi minus xj to sigma square. So this is the popular one, that the Gaussian kernel. And maybe also we can consider the sigmoid kernel. Sigmoid function also we can consider. So these are some examples of kernel functions. So based on this we have to formulate the Lagrangian dual problem, because we are considering the nonlinear support vector machine and we have to solve the optimization problem. So for solution of this optimization problem, the formulation is important, that already I have discussed. In case of the linear support vector machine, we have to consider the Lagrangian dual problem. So move to the next slide. That is the nonlinear support vector machine. And we have to consider optimization. So like in case of the linear support vector machine, we have the formulation. This formulation is, that is the Lagrangian dual problem. The formulation is maximize summation I is equal to 1 to n, summation for all the support vectors, because alpha I we are considering alpha I is not equal to 0. So for support vectors alpha I is not equal to 0, 1 by 2 summation I is equal to 1 to n, and also we have to consider j is equal to 1 to n, alpha I, alpha j, yi, yj. Now we have to consider the kernel function k, xi and xj. So this is the kernel function we are considering. The conditions already I have explained. The important condition is such that this alpha I should be greater than equal to 0, and another condition I is equal to 1 to n, alpha I, yi should be equal to 0. So from this I can determine the discriminant function. So discriminant function is gx will be equal to summation. We are only considering the support vectors, because support vectors are the most informative points of the training data set. So alpha I is nothing but the Lagrangian multiplier, and we are considering the kernel function. K is the kernel function. So you can see we have to consider xi. Xi is nothing but the support vector, and x is nothing but the test sample plus b. So we are obtaining the discriminant function. So this optimization technique is the same technique already we have discussed in case of the linear support vector machine. So we can obtain the expression for gx. So this is the expression for the gx in case of the nonlinear support vector machine. So only we are considering the kernel function k, that is between the support vector xi and the test sample x. So for this algorithm, the nonlinear support vector machine, so what are the steps I need to consider? The steps will be like this. So for this nonlinear support vector machine, what are the steps? So nonlinear support vector machines. So first I have to select the kernel function. Choose a kernel function. So generally we considered the radial basis function, or that is the Gaussian kernel we can consider. Number 2, we have to solve the quadratic programming problem. That is actually the optimization problem. And number 3, because after solution of this nonlinear optimization problem, we have to determine the weight vector, and based on the weight vector we can determine the discriminant function. So construct the discriminant function from the support vectors. So these are the steps of the support vector machine, and the kernel generally we consider the Gaussian kernel or the radial basis function we consider. So in this case you can see in the expression for the nonlinear support vector machine, we obtain gx, that is the discriminant function, that is something like this: w transpose phi x, that is the mapping function, plus b. So it is equal to summation. We are only considering the support vectors alpha I phi xi transpose. Already I have shown this expression, phi x plus b. So in this expression here you can see we are considering this part, that is the mapping function we are considering. So in the linear support vector machine, if you see, I considered the dot product between the support vectors and the test sample. In this case we are considering the mapping function. The mapping functions are phi xi and phi x. But in this case, since we are considering the dot product, we do not need to represent the mapping explicitly. So that means the mapping is not so important, because we only consider the dot product. So we do not need to represent the mapping explicitly. So that is the dot product between phi xi and phi x. So that is why with the help of this dot product we can determine the discriminant function. So we need not consider to represent the mapping explicitly. So this is the fundamental concept of the support vector machine. So briefly I have introduced the concept of the nonlinear support vector machine. In this class I have explained the concept of the nonlinear support vector machine. I have explained what to do for the nonlinearly separable data. So the concept is, if the training samples are not linearly separable in a low dimensional space, I have to project them into a higher dimensional feature space. In the low dimensional space, the samples are not linearly separable, but in the high dimensional space, the samples will be linearly separable. So I have to define the mapping function, and based on this mapping function, I have formulated the optimization problem. So we have defined the Lagrangian dual problem, and based on this solution of this, we have obtained the weight vector W. And after getting the weight vector W, we can determine the discriminant function Gx. And with the help of the discriminant function, we can do the classification. So this is the fundamental concept of the nonlinear support vector machine, which is almost similar to the linear support vector machine, except the concept of mapping. And for multi-class classification, we may extend these principles, the principle of the support vector machines. Also, we can consider the principles like one versus one classification or one versus all classification techniques for multi-class classification. And that concept already I have explained, the concept of one versus one and one versus all classification techniques. So this is about the support vector machine. So let me stop here today. Thank you.